No, we'd like to have this talk with Takis.
Yeah.
Okay, no need to introduce Takis and
Okay.
yeah, so let's start.
Thank you very much for coming to the last minute talk, which was only announced yesterday. No, I'm not allowed to. No. Later, after the workshop, I can do it again if you like. But no. Oh, are you okay? So what I'm going to talk about is a class of let's call them stochastic directed graphs. So these graphs apparently appeared for the first time in this paper. I'm going to give you I have a list of references here. Of course, I have to keep interchanging. But no. It's okay. It's okay. It's for me to remember. Okay, just to point out the paper to you. Okay, there is this paper by Barak and Erdős, 1984, on the maximal number of strongly independent vertices in a randomized cyclic directed graph. Okay, so this is the earliest reference to these graphs, and I'll say what they are using our terminology. So we have the integers, and it's a directed graph. It's always directed from left to right. We take two integers I and j, I smaller than j, and then we toss a coin whose probability of heads may depend on I and j, and if heads, we put an edge directed from I to j. If tails, we don't. Okay. So this is the model. If tail, nothing. We just don't do anything. So we put edges only for the coins that show heads.
This is for every pair?
We do that for every pair. So for every I, j with I smaller than j, we have random variables alpha I, j that take values 1 or 0, but I'm going to call 0 minus infinity. I prefer it this way. And the probability that alpha ij is equal to 1 is some function of the distance. Okay. In the simplest case, the paper of Erdős and Barak, so that's what I'm going to call simple case, is pi equals to p for all I. Okay. So this is a directed version of the Erdős-Rényi graph. That's what it is. Now, just to talk about application, this has several applications. One is in parallel processing systems.
You're not requiring any summability or anything then?
I'm going to assume many things, but I'm not assuming anything for the time being. Okay.
Okay.
Yeah. You see, because depends what I want to prove.
Okay, exactly. You're not going to be able to do much with that one.
With that one?
Yeah.
What do you mean I'm not able to do much? Yes.
Because you're not going to be able to solve it.
I mean, we first. There is.
Because you're not going to be able to construct the process.
I'm able to construct many things. It's also there is a paper by Voss here and myself, 2003. That's like 50-something page long. So we do something there. With the case pi equals p. So just depends on the problem, depends on what questions you're going to ask. Okay? So parallel processing systems. This is the old story where you have a queue, you have a buffer, and you have customers that arrive here. Sorry, let me not put it this way. Let's say that we have an infinite number of servers, as many servers as you like. And you have customers which arrive according to a Poisson process, let's say. If the customers, there's no constraint between the customers, then an arriving customer will find an empty server because we have an infinite number of servers and get served and go away. Okay? Or we can have a precedence relation like this. Customer I is restricted from the previous one, and so on. So in which case, this customer cannot start before this customer finishes, and so on. So there's no use of having more than one server. Okay, that's a first come, first served queue. Okay. More generally, you can have some kind of dependence, some kind of partial order that shows who is restricted by whom. Okay, so this is an in-between case between the first come first serve and between the infinite server queue. Okay, so if we ask what is the stability condition of such a system, well, if we have service rate, let's say 1, so service rate 1, then we can saturate the system with a large number of customers and then see what is the rate of emptying the system. If that rate is smaller than 1, then the system is stable. If it is larger than 1, it is unstable. Okay? The rate at which the customers go out, if we saturate it, is the longest path, the length of the longest path between node 1 and node n. Okay? So we know that this length has an asymptotic linear growth because of subadditivity. So that's the stability condition in abstract. So the question is, what is this constant? What is this rate? So this appears there. Second, in so-called community food webs. That's not an area I know about. This is mathematical ecology. And several people have worked in this area. And the book has been written at some point by Newman, Cohen, and so on. I don't know who the author of the book is, one of them. Cohen, Newman, Cohen, and so on. Okay. So what happens in this area? You have a population in an isolated island, and you have species, and you know who eats whom. Okay. So you eat, I don't know, beef eats vegetables, and so on. Yes. No. And so on. So the survival of the population depends on the longest path from the lion, or from Sergei, let's say, to the microbe.
Like
just okay. So people are interested in this thing in this different area, and it also appears in statistical physics, but I don't know much about it. Okay, so so what I want to talk about eventually today is an extension of this model, which looks like this. So this is a big picture. No worries. There's a lot of draft here. Okay, let's put it like this. It's supposed to be a three-dimensional picture. So we have a random graph on a partially ordered set. This partially ordered set is the product of two spaces. The horizontal space is Z. The vertical space is I, which is itself a partially ordered set. So you see here, these diamonds here are supposed to be slices of the vertical set, the set I. So we have the set Z, which is ordered according to the natural order, and you have a partial order on the set I.
I'm sorry, you're not saying what I is.
I'm going to say in a minute what the assumptions are. I could be, for instance, 0, 1, m. Okay, case 1.
it's finite set.
It's a finite set to start with, yeah, with a natural order. Okay. Second, I is a partially ordered set that has, I'm going to assume that it has a minimum, so 0 is comparable and smaller than every element of that set, and also every element of that set, how am I writing this is partial order, I'm not good, than some maximal element m. So we have 0, we have m, and we have some kind of partial order, perhaps represented by the so-called Hasse diagram of the partial order. Hasse diagram of the partial order is a graph, is a directed graph, such that if you have, if this is smaller than this and this is smaller than this, then you eliminate this because this is implied by this. So you eliminate implied edges in order to get the Hasse diagram of a partial order. And that's important when I formulate the limiting random variable, and I'm going to call the Hasse diagram like this. Okay, so it's a directed graph. It has a maximum, it has a minimum.
Is it obvious that it's unique?
The Hasse diagram? Yeah, it is.
And I haven't even thought about it.
Yeah. It's a standard order theoretic notion. Yeah. For example, you can take a number and look at the Hasse diagram of all the divisors. If you take 2010, for instance, you can find all the divisors. I don't know the way, so it has 2010 is 2 times 3 times 5 times 67, right? So it's yeah. No. It's
Can I say something?
yeah.
Can I say something really nice now?
Yeah.
So 2010 is 2 times 3 times 5 times 7 plus 11 plus 13 plus 17 plus 19.
Say it again. Say it again. You're too quick for me. 7.
7 plus 11 plus 13 plus 17 plus 19.
Plus 19. Okay.
That's 17.
You forgot
17 plus
17.
19. You take the first 8 primes and
The
you
first 17 plus
plus 19.
plus 19.
That's
Wow.
the-
That's great.
Now you recommend a math meeting.
This is. Are you doing numerology or something by any chance, or are you into numerology?
Wait. So what?
So this was an example. This was an example.
2010 is 2 times 3 times 5 times.
Okay.
Right. Okay, very good. So, for example, if we take divisors and then we put this divides this, 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 and so on, okay, you get the Hasse diagram of the partial order in the set of divisors of 2010. This is actually a graph that has a constant degree equal to 4. If we don't count. Okay, fine. So, for instance, you can think of that as I. Right, so what do we do here in this set? We take, so this is I, this is Z, and we have a partial order like this here, and just a natural order, and then we put component-wise order here. So we say that xi is smaller than yj if x is smaller than y, or smaller than or equal to y. I precedes j in the partial order, so in particular I must compare to j, okay? And the two things are different. Okay, so you have such kind of thing. And then you put an edge from xi to yj with probability that depends on these 4 numbers, okay? So we will have random variables xi, yj. The probability that this is equal to 1 is some number which we want to depend on the difference y minus x to have translation invariance here, and separately it may depend on I, it may depend on j. Assumptions will follow. So this is the graph. In particular, these probabilities could be equal to p.
So it's strange, you put y and x for z.
Yeah, I do that. I keep shifting notation. That's right. So you have to excuse me when I use letters. Sometimes I use x, sometimes y, sometimes I, sometimes j, sometimes u, sometimes v. I haven't fixed my notation because I worked on this thing at different times last year, and then I have different frames of mind. Okay, so yeah, keep into. So everything is integers here. I'm not using real numbers. So all letters are integers. Okay, so so what are we interested in? We're interested in taking some element down here and another element up there and finding the length of the longest path. Okay, if they are connected, okay, because there's a probability that these are not connected. So if they are connected, we want to find the length of the longest path and find asymptotics for that.
So what's the definition of a path?
Definition of a path is a sequence of vertices. Let's call this vertex V. Let's call this vertex U. Sequence of vertices V1, V2, Vk, such that this is an edge, this is an edge, this is an edge.
So you're not allowed to retrace or anything.
Not allowed to?
Retrace. I mean, it's
No, no.
it-
It's increasing. It's increasing. So in this sense, it goes. It can go here like this. It can go vertically. It can go like that. It can hop like this. But you're not allowed to go down or back. Always increasing. Okay.
And the first point contains the minimal element, and the last point.
Yeah, that's right. That's right. I'll show. This is not necessary, as we will see that. That is not necessary because under our assumptions, this will be connected almost surely when n is large. Okay.
has to be increasing in both Z and I or only in Z?
Yes, it has to be increasing on both.
No,
Yeah.
no, no. You said that you have the edge if one of them isn't.
Right. So we can have xi to xj. That can be an edge with the same x. That can be an x. It's not too important. We do this. We make this assumption for convenience. In fact, if you like, we can make a little bit of backtracking as long as this backtracking is bounded. But we won't because, you know, things become complicated. Okay. I just said two motivations here. Okay, longest path. These problems are also related to last passage percolation problems, except that this is not a nearest neighbor graph. Okay, so whatever motivation you have in last passage percolation, you carry through here, but also you have these applications, as
You
I
can
said.
see the horizon n in z, in the first direction, divided by n. So n, take a longest path, divide by n.
I'm going to say that. I'm going to say that. Okay. So so before I do anything for the partially ordered graph, I'm going to say some things about this graph here. Okay. So let's see. Let's give some definition. So I have these numbers pi. I'm going to make one assumption, namely that p1 is positive. That's assumption 1. Okay. P1 is positive. There is always probability to connect to the next vertex. This is not important. What we're going to do is identify some kind of renewal structure. And if we don't have this assumption, the process we are going to find, which is a random subsequence of the integers, may not be renewal, may be one dependent somehow. So, because we don't want to work too hard, we're lazy. So this is a laziness assumption, P1 positive. Okay. Certainly, we can work with the case where Pk is positive and k is the smallest thing, and then we have some k-dependent structure. So P1 is positive. All the numbers, yeah, okay, that. Second assumption I'm going to make is that the sum of 1 minus P1 and so on, 1 minus Pk, for k equals 1 up to infinity is finite. That's my second assumption. You'll see where it comes from. And there is a stronger assumption sometimes, which he says multiply this by k and assume that it's finite. This is somehow a finite mean assumption, and the second one is a finite variance assumption. Of course, these assumptions are satisfied when the pi's are all equal to p. Okay.
It's yours.
No, unfortunately, it's not. And I was trying to eliminate these previous traces because I feel embarrassed. Look how neat this is compared to mine. So I should completely erase it. This is, okay. By the way, so let's do this. Let's say that we define as Tij as the length of the longest path that starts from I and ends in J. I think I took the notation from a paper of James Martin. It's your notation, I think, to call it Tij. Okay, it's so this is the maximum length of all paths starting from I and ending in J. Now, when we have a nearest neighbor graph, this Tij is a superadditive quantity. You want to go from I to k. Well, if you condition an intermediate node, the maximum to go from I to k is larger than the maximum to go from I to j plus the maximum to go from j to k. Now, you don't have that here precisely because you don't know whether I and j may be connected. Okay, so this is not a superadditive quantity. It's not subadditive either. So we want subadditivity. So what do? We relax this and say define Lij to be the maximum length of all paths from some I prime after I to some j prime before j.
Inequalities.
Yeah.
It's okay. It's okay.
Yeah. So if I and j are here, okay, so take the maximum path that starts from somewhere after I and ends somewhere before j. Now,
This still could be infinite, right? Because there could be no edges in between.
Positive.
yeah,
Positive
that-
part.
right, that's 0. Put all 0. Right, that's true. That's true.
Positive.
So here we have a subadditivity condition, namely Lij or Lik is smaller than or equal to Lij plus Ljk if I is smaller than j smaller than k plus 1. Why is that? It's because if you have the maximum path from I to k, you split that into a part that belongs in this graph, part belongs in this graph. If this node is contained in the maximum path, you don't need the 1. If it's not contained, it may cross like that, so you need an extra 1. Okay? So Lij is a random variable that has this subadditive property. Of course, Lij is at most j minus I, so you have no problem with expectations. The distribution of Lij is the same as the distribution of Li plus k, j plus k. So you have a shift invariance, and therefore Lij divided by j, the limit as j goes to infinity exists, let's call it j minus I, and it is equal to the infimum, like that, the infimum of the expectations, in fact, and that's a constant, okay, that depends on P1, P2, and so on, all this sequence. Okay, so this is the constant we'd like to identify, or would like to say something about. Now, in the case where all the pi's are equal to p, we know what this constant is like, and this is the first picture. Okay, so this function here is the constant c as a function of 1 minus p. 1 minus p. In a paper we published a few years ago, we have explicit bounds for this constant, and the explicit bounds are plotted here. So the function is somewhere in the yellow line, in the yellow area. Okay, I mean, don't look at these functions. I'm only showing them to you to tell you that I can compute it explicitly, and that these bounds show that the function c of p is not convex. It is above the diagonal, and it is not a convex function. It starts from 1, it goes down to 0. I'll say in a minute a couple of words about the method for obtaining these bounds rather than showing these functions. So the corollary is more important, that as q goes to 1, this constant is of the order p log p. In fact, it is known by different methods that it is asymptotically equivalent to p log p when p goes to 0. And as q goes to 0, the function is 1 minus q plus q squared. Okay. The upper bound and the lower bound actually here match all derivatives, so they're very sharp here. Okay. So that's what we did a few years ago, and
Still strictly bigger.
okay.
This constant is strictly bigger than p.
The constant is strictly bigger. That's what I said. It's above the diagonal. That's what I meant. It's above the diagonal. Diagonal is below that. So 2 minutes about the methods for getting these bounds. I'm obviously not going to derive them because it takes quite a bit of work, but I'll say a few things. So to get these bounds, we start growing the graph vertex by vertex. Okay. So we start with 0, 1, 2, 3, and so on. We start putting vertices. I'm referring here to the case where all the pi's are equal to p, strictly between 0 and 1, and q is equal to 1 minus p. Okay. So let's say we have created the restriction of the graph between here and here. That means we have tossed our coins, and we have seen that we have, let's say, things like this, maybe this. Okay, so that, and we want to put a new vertex now. We are interested in the longest path. So the longest path will increase by 1 if we connect to the heaviest vertex, meaning to the vertex that has the longest path width. So what is the longest path ending in 1? It is 1. It's just 1. Here, it is again 1. Here, well, let's make it a little bit more interesting. Let's make this, it's 1, 2. Here, it is 3. Here, it is 1. Okay? So if I succeed connecting the new vertex to 4, then I have increased the longest path by 1. Okay? I'm tossing coins, so it doesn't matter which order I'm connecting to. So I may as well keep track of the weights of the types of the vertices. So let's say that this is vertex n and this is vertex n plus 1. So we have vertices that have weight equal to ln, the longest path between 0 and n. So let's call ln to be the longest path between 0 and n. Okay, so how many such vertices we have? Well, I don't know. Let's call them xn of 0. Now, look at number of vertices that have weight ln minus 1. I have xn minus 1. In this case, I have 1 of type 3, 1 of type 2, then length ln minus 2, xn minus 2, I have 1, 2, 3, and so on. Okay, so this is my state at time n. So my state at time n is a vector of types. Okay, is it clear? So, right, so to go from xn to xn plus 1, I just use IID random variables. In fact, it's a geometric random variable, so it's a Markov process. It's a Markov process on the set of strings. So this is Markov. So it is Markov in an infinite dimensional space, and in fact, it converges to a unique steady state, which is an infinite vector, and it converges very strongly, namely it couples with the stationary version. All right? So once you know it couples with the stationary version, you can work with the stationary version, and you can write balance equations for the stationary version. And then say, well, how am I going to increase the length by 1? I'm going to increase the length by 1 if I connect to one of the vertices that have maximum weight. So the probability that I do that, I use a geometric, yes?
Is it obvious that it converges to stationary version? Why is it obvious that the number of
it's
optimal...
Nothing is obvious. Nothing is obvious. I'm just saying that it happens, and there is a theory for that. In fact, what we use is we use so-called renovating events, like an extension of the theory of renovating events in order to prove that.
So for each fixed k, xn of k converges to some...
Not only that, I'm claiming that this as a vector converges in total variation distance to some infinite dimensional vector in the big space. Okay.
Not the whole vector, only projections.
Yeah, projections, but I was going to define a weighted distance in order to, a 2 to the minus k weighted distance, so that's in that sense. Okay. Right? Okay. I mean, it's not obvious. You have to show that it converges and then work with the stationary version, write balance equations to get something. And the thing that results into these inequalities is this. If we call this function C of Q, we can show that C of Q is smaller than or equal to 1 minus q divided by 1 plus q over 1 plus q times c of q squared to get an upper bound. So you iterate that to get an upper bound, okay?
What is it, C of Q?
C of Q, what is C of Q? C of Q is this constant, and you will forgive me because sometimes I write the C of P, sometimes the C of Q. I'm very sloppy.
Q is always 1 minus P.
Q is always 1 minus P, that's right. Yes?
You can infer C of Q from the stationary measure of this process, right?
That's right, that's right. So this inequality, in fact, is equality, is balance equations, and there are terms in the balance equations that we cannot estimate, so we drop them and we get an inequality.
But you can write equality.
Eh?
C is 1 minus
Yeah, it's okay. It's just the most important part is this, yes. So I don't want to speak more about this. Is that okay? So basically what I said is that there is a way to get a Markov process, show that it converges to a stationary stationary process strongly, and then write balance equations to get bounds. Okay, so excuse me, it's okay, we can talk about it later. Now I'm going to go back to the graph, which is the inhomogeneous graph. The PIs are different. So the problem we're looking at is not estimating the constant because, well, that's a function of infinitely many variables. We don't even know how to address this problem. But so we're going to look at some laws of large numbers and central limit theory. In fact, what I want to show is, let me write the result. If I find what happened to this. There it is. Okay. So let me write the result. So, as I said, ln divided by n converges to some constant. This happens both for the one-line version and the multi-line version. Okay. ln divided by n converges to some constant. So I'm going to write the central limit theorem associated to that, and this is what takes a while to prove. The central limit theorem says that if we look at ln, and now this is the only instance where I use a real number. This t is a real non-negative number. Subtract c and t and divide by some constant, which is a variance type of constant, divided by a square root of n, and consider this as a process that converges weakly as n goes to infinity to some zt, which is defined as follows. So zt is the maximum of some other processes which are indexed by the letter iota. It's a Greek letter iota. It's not the square root of -1, as we said there. It's just a letter iota. It's a maximum over iota, and iota are, there's a t here, are paths in the Hasse diagram of this. Or actually, let's call it z iota of t. And what is z iota of t? So I'm going to fix a path. So let's say this is a path of length r. Okay, so these are elements of the vertical space I, which are comparable, and this is smaller than this, smaller than this, smaller than this. And this is written as a supremum. I'm going to take r plus 1 Brownian motions. So for each of these things, I'm going to take a Brownian motion bi0, bi1, bir. So these are IID standard Brownian motions. And I'm going to take bi0 evaluated at some time t0 plus bi1 t1 minus bi1 t0 plus, and so on, plus bir tr minus bir tr minus 1. So the supremum here over all so I take the interval 0t, I split it according to times t0, t1, tr. So this is 0, this is t. Let's say I do like this. Then I evaluate the first Brownian motion, the increment of the first Brownian motion here, plus the increment of the second Brownian motion here, the third Brownian motion here, the fourth Brownian motion here. Take supremum when these numbers fluctuate between 0 and t. Do that for every path of the Hasse diagram, and then take maximum over all paths. Okay? So that's the limit. in the special case where I is equal to 0, let's say 0, 1, so it's a two-element set, let's call that 0, 1, then what do we have? We have B0, let's call that S, plus B1T minus B1S, and then I take supremum 0 less than T. That's my ZT.
Excuse me, Takis,
Yeah.
I got a bit lost
Yeah.
here. What is the motivation of the B's here?
The motivation of the B's are Brownian motions.
Yeah.
And okay, I'll show you the motivation. If we are in the single line case, okay, we're going to get a Brownian motion. It's an ordinary central limit theorem. We are in the multi-line case. It's parallel lines, the slab graph, as we call it. So to get the central limit theorem in the slab graph, we have to take many independent Brownian motions and then take suprema of sums of increments in order to get a central limit theorem. So once you put a second line, you need to get a second Brownian motion. Okay, so this is an important random variable that shows up in many other applications. So this is 0, 1. So let's take this case. The vertical space is a two-point space from 0 to 1. Okay? Now we take a Brownian motion here, a Brownian motion there, and then take the increment between time s and 0, b0, 0 is 0, and then the final increment of the other Brownian motion, add them up, and then take supremum. That's ZT. Okay, so I claim that this ZT is the functional central limit theorem for the length of the longest path. Okay? Now, this is a famous distribution because of the following. Let's take t equals 1. Of course, there's some self-similarity here because z of lambda t is equal to, oops, oh, that moves, okay. Yeah, is equal to square root lambda zt in distribution. So if we take z equals 1, this z1 is the distribution of the largest eigenvalue of a 2 by 2 Gaussian unitary matrix. So if we take a matrix, so what do we mean by Gaussian unitary matrix? I take a matrix that has, so perhaps I should call them 0, 0, 0, 0, 1. It's a matrix of complex random variables, and I'm taking it to be, let's call this matrix A. A star is equal to A. So this random variable here is the complex conjugate of this random variable. And therefore, the random variables zeta 0, 0, zeta 1, 1 are real random variables. And they are IID normal 0, 1. Okay, so this is IID normal 0, 1 in R. IID normal 0, 1 in R. And this is standard normal in the complex plane. Okay, so zeta 0, 1 is, let's call it x plus square root minus 1y, where x and y are not standard normal, but they have variance equal to 1/2, so that the expectation of zeta, that's what's called standard normal in the complex plane. Okay, it has two real eigenvalues. The largest eigenvalue has distribution z1. Okay, you do the m by m case if you have a linearly ordered set I that for the vertical space. Okay. So in fact, this observation that people knew about distributions of matrices of that form a long time ago. By the way, the set of these matrices is called the Gaussian unitary ensemble because it's invariant under unitary transformations. U, A, U inverse belongs to the same ensemble. That's why it's called unitary ensemble. It's invariant under the group of unitary transformations. So in physics, they knew about these matrices a long time ago. And at some point, Freeman Dyson wrote a paper who explained, this is this paper, Dyson 1962, Brownian motion model for the eigenvalues of a random matrix, who explained that, look, you can get the largest eigenvalue by taking independent Brownian motions, starting from different points, and condition never to hit one another, so to stay ordered. Okay? So that's what he did. And in fact, he did it not only for variables with Gaussian entries, but also with quaternion entries. So yeah, so never to intersect. And so that was the first paper that showed this connection. After that, there have been other papers that explore these things. For example, this paper of Baryshnikov in 2001 that is called Gu's and Q's, GUEs and Q's, shows that you can get this distribution if you have Q's in series, and if you get Q's in series and look at the departure process, corresponding Brownian motions, and so on and so on, they behave like Brownian motions that never meet one another, and you take limits. So that's the closest to our area here. And this paper, I think, was motivated by the paper of Glynn and Witt, 1991, which is called Departures from Many Q's in Series. Is that correct, that Baryshnikov's motivation was that? So that's the order of events. These kind of functionals show up in many areas. For example, if you look at a finite alphabet and start of ordered letters, let's say the letters are 1, 2, 3, 4, 5, n, okay, and start drawing IID random variables from that finite alphabet, and look at the long sequence of these IID random variables, and then look at the length of the longest increasing subsequence. Now, you can write the longest increasing subsequence as a functional of the sequence, and that functional resembles this. I mean, if you write it down, it takes a while, you will see this. And once you see this, then you can prove the central limit theorem. Okay? So people have done that for IID letters drawn from an ordered set. More recently, they've done it for letters drawn from a finite set. Oops. Is it working? Hope I haven't. According to a Markovian process. And this is this paper by Houdre. Did I do? Yeah, I dropped that. This paper here, I only have the archive version of it, on the limiting shape of the Markovian random Young tableau, looks at this functional for sequences that form a Markov chain drawn from a finite alphabet. So, why I'm saying that? Because we can do things, central limit theorem, that is, even when we allow some dependence between edges. Okay? All right, so this is the result. Now let's see. How do we get this result? The hardest thing in getting this result is finding a central limit theorem for one line. Once you find the central limit theorem for one line, and you write a function, then you apply, continuous mapping theorem, whatever, to get it for many lines. It takes a little bit of work to write it down carefully, but the most important thing is to get it for a single line. Now, so I should convince you in the next 15 minutes that we can get it for a single line. Okay, so here are the ingredients. So I'm claiming, so back to this graph, I have P1, P2, and so on. I have P1 positive, and I have this condition.
They're here. Takis. This condition.
Yeah, they're there. Okay, that's right. Fine. 1 minus pk, k equals 1 up to infinity finite. In fact, I'm going to assume something stronger now, just to be safe, that I have this condition. Okay, so it's this random graph that you see here. Now, whenever you have a random directed graph, you have a partial order. What's a partial order? The partial order is, I'm going to denote it by I squiggly arrow j, meaning there is a path from I to j. Okay? So this event is, there is a path from I to j. And that's a partial order if there's a path from I to j, and from j to k, there is from I to k. So this is a random partial order. That's my point of view now. This graph induces a random partial order. This was actually the point of view of the paper. Here there's another paper that worked on the Barack-Erdős graph. That's not Barack Obama, some different Barack. And this is the paper by Alon, Bolobas, Brightwell, and Jansson, 1994. Linear extensions of a random partial order. This paper looked at a finite chunk of this graph, said this is a partial order. A partial order can have many linear extensions. That is, a linear order that respects a partial order. How many? They found that of linear orders extending this partial order restricted on 0, n. Okay? They found that it's not difficult to compute the expectation of nn. The expectation of nn is precisely equal to the number of inversions in a random permutation of length n. And this is product 1 minus q to the k divided by 1 minus q, k equals 1 to the n. Actually, they only work in the case where all the pi's are equal to p. They find this.
I don't understand your definition of n.
You don't understand the definition of n?
What do you mean by linear
Yeah,
order?
okay, so let me give an example. Let's say I have 4 points, 1, 2, 3, 4. So I go, let's say I have from 1 to 3, from 2 to 4, from 1 to 2. Let's just take this partial. That's a partial order now, okay? So 1, 2, 3, 4 is an extension of that. Because 1 is smaller than 2, it's smaller here. 1 is smaller than 3, here. Okay, but 1, 4, 3, 2 is not. Yeah? Because in this is 4 smaller than 2, but here 2 is smaller than 4. Okay? So you have permutations of 1, 2, 3, 4 that respect the partial order. How many such permutations?
So for this one is only one. For this one is only one
It's
extension.
also no. This is
3 and 4.
1, 2, 3, 4. 1, 3, 2, 4. Okay.
Is one able to say more than just things that an expect?
Yeah. That's the whole thing. It grows exponentially. So this is, what is this? This is 1 over 1 minus q to the n times this product times a constant. No, sorry, that's a different constant. Let me call this constant square root of lambda. Square root, that's what we call in the paper. Square root of lambda. Therefore, the logarithm of nn, okay, does something. In fact, the logarithm of nn satisfies the central limit theorem. You subtract constant times n, divide by some square root of n, and that converges to normal random variable. So that's what they do in that paper. It's a nice way to see why this grows like this, but I'm going away. This behaves like a branching process, in fact. You can write n plus 1 as a number of geometric random variables, the number being nn. So nn plus 1 is like the sum of yi for I equals 1 to nn, and these are geometric random variables, something like that, actually minimum with n. So once you see that it grows geometrically, and so the problem becomes that of the branching process, essentially. Okay? So, so go back to our problem now. So we don't want to find linear extensions of this partial order, but we want to find a subset. It would be a random subset that has a property that is linearly ordered. What does this mean? It means there is a path from here to here, and from here to here, and from here to here, and so on. That's a linearly ordered subset. Moreover, we want this subset, the elements of this subset, to be comparable to everything else. Okay? So this means that there is this from here, there is a path to here, and to here, and to here, and to here, and everything else. Okay? So not only this is a chain, but it compares to everything else. We call this subset a skeleton. Yeah?
I don't understand.
Yeah. Okay. So I want to find, perhaps there are vertices, okay, that have the following property. Let's call these vertices x. There is a path from everything to the right. Everything. So I can reach this point, I can reach that point, I can reach everything. And this can be reached from everything from the left. Okay? Such a point, I will call it a gold point, if I can find it.
Connected with everybody else.
Yeah. like we call it a gold point. The collection of gold points is obviously linearly ordered. Not only that, but they also compare to everything else in this partial order. Okay? Okay. So these are the gold points. So I can define such a point, say that S is the set of gold points. We also call it skeleton. Which is defined as all n in Z, such that n, there's a path from n to m for all m larger than n, and there is a path from m to n for all m smaller than n. Okay. The randomness here, the omega is here. This is the omega, is a partial order. Okay. If we show that this skeleton exists, then it doesn't take too much to realize that this skeleton is a renewal process. Okay? Yeah.
So you need some conditions to ensure that it's non-empty. Is it the summability
I have put the conditions down.
Summability
The conditions. The conditions are these.
implies that you have a golden set non-empty and
Right.
comparable.
Yeah.
If it's not
That's right.
empty,
That's right. So in particular, if all the pi's are equal to p, then these conditions are satisfied. I put this extra condition because this will allow us to get finite variance to get the central limit theorem.
So what is the definition of comparable?
There is a path, this is it. I compares to j, in particular I leads to j, if there is a path from I to j in this random graph. You can reach j starting from I in a number of hops, not necessarily directly. Okay. So, in fact, under these conditions, what I'm claiming is that S is a stationary renewal process. Stationary renewal process means that, accepting the interval that that contains 0, everything else are IID random variables. Okay, you can compute the distribution of that in relation to the others, and that if you shift the origin to any point, the distribution of this object does not change. It's a stationary renewal process that has a rate lambda, and that's the product of 1 minus q. Sorry, in this particular, it will be 1 minus p1, 1 minus p2, 1 minus pk, k equals 1 up to infinity, squared. That's why I call the previous constant square root of lambda, because lambda is the rate of my renewal process, and I prefer to think of the rate. Okay, okay. So that's what it is. Okay, not much time left. So I want to say, yeah.
Why, you're defining this to be lambda.
I'm defining this to be lambda, and of course,
because you use square root of lambda there without the squares. Why are you defining that as the square root and lambda as the square thing?
I meant, what did I mean? Let's see. What I mean? Yeah, that's a good point. Yeah. So what do I call it? I mean, well, that's fine. Yeah, because if the square root of lambda is this infinite product, and that's what is here.
Yeah, but I mean, why define it that way? Why not define lambda as the thing without the square?
Well, okay, we're talking about that.
No. I mean, there's probably a good reason.
Yeah, the reason is because I like to think of the rate. I mean, in central limit theorems, it's the rate that enters there is a lambda in whatever I'm trying to do, and I don't want to write square root of it. That's all. There's nothing. Okay. So the hardest thing here is actually showing that we have finite variance. And in order to show that we have finite variance, we must do a construction to construct a gold point, to show that we can find the gold point. Now, to find the gold point, I'll make a long story short. So, look. let me define the following event. A plus ij means that I connects to j, to I plus 1, to I plus 2, and so on all the way to j. So I have j, and I can reach here, 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 here. Okay? So that I call A plus ij. And A minus ij means that I can reach j from j minus 1, from j minus 2, and so on from I. Okay? So what is a gold point? A gold point is a point that will satisfy the following conditions. It will satisfy the condition A plus I. A plus I means basically go all the way to infinity, j greater than I of A plus ij. And it will satisfy the condition A minus ij, A minus I, which is the intersection A plus ji, j smaller than I. So if we look at those i's for which indicator, let's say A plus I intersection A minus I is equal to 1, that's precisely the skeleton. Okay, so we have a way to write the skeleton in terms of these events.
Yeah.
Right?
AJI minus on that intersection.
That's A minus, yes, thank you. Thanks.
This decreases.
So,
it decreases.
right, so they both so if I increase the right index, it decreases, or if I decrease the left index, it decreases, so that's why I'm taking intersection in both cases. So a point I is a point of S if this is equal to 1. Okay, the probability that point I is a point of S is the probability that this happens and this happens. They are independent, so it's the product of the probabilities. Okay, the two probabilities are the same, and that I call lambda. So square root of lambda is the probability of A plus I or A minus I. Okay, so here is the construction. The construction is actually difficult, and I'll try to explain it by picture. Here is 0. I want to find the gold point. Where is the gold point? The first gold point I can find, to the left of 0. Well, let's be modest, okay? I mean, we want to find a point that connects to everything to the right and is connected from everything from the left. Let's find the first point that connects to everything up to 0. Okay, I'll put a dot here. Well, I can find that. That will happen in finite time. In fact, it will have finite expectation. I can find that. Okay, if we had more time, I could give you an argument for that. That's the first point. Now, I check. Does this point, is everything from the left connected to this point? Well, I start checking, and perhaps I will fail at some point, and this is the first point that is not connected to that. Okay? If that happens, then try to create another such point from the left. Okay? Actually, let me represent the event ij, A plus ij. I'm going to pictorially represent it like that. Why? Because if A plus ij and A plus jk, then A plus ik. See, it's just pictorial. And A minus ij, let's represent it like this. So that gives me a little bit of geometric thing because. So I have achieved that. That's the event that happens. Okay, here I have failed to connect to everything to the left, so I try again. Okay, I will find another one for sure that connects up to here. And if this connects to everything within here, then it connects to everything up to here. Okay? Now, it so happens that this random variable, which means fail to connect from everything from the left, will be infinity with positive probability. That probability is going to be square root of lambda. Okay? So at some point, let's say here, I have reached infinity. That happens with positive probability. I say great, because that's now a silver point. Silver point because it connects from everything from the left. Okay? Now I've done that. I've done that once. I found a silver point. Once I found a silver point, I can keep going and find another silver point. Okay? So here is another silver point. I keep repeating this process. Okay? So here is another silver point that has been reached in a number of steps. As I said, another silver point. Okay? Now, this silver point is better than this silver point because it includes more, it connects farther to the right. Okay? So I have the sequence of silver points. That's silver point 1, silver point 2, and so on. Okay? Now, if I check what else, what extra I need in order that I get a gold point, I see that one of these silver points must be gold with probability 1. So I pick the first gold point among these silver points. Okay? So I keep creating points like that, and lo and behold, at some point I will find the gamma 0. And that's my first point of the skeleton before 0. So once I have that, having done that, I know how to find the variance of gamma 0. The mean of gamma 0, the variance of gamma 0, I know how to find the variance of gamma 0 because I can write that as a geometric sum of IID random variables. It's in distribution equal to that, okay? Using a standard thing about ladder heights, or what French called the coupage de Lévy. And once I have that, then I get the variance condition I wrote to you down in order to get the central limit theorem. Okay, so I think I'll stop here because we need to finish. Thank you.